Alright, thanks for watching. And so far in our matrix adventure, we've seen that matrix multiplication comes from composition of linear transformations. And that the inverse of a matrix comes from taking the inverse of a linear transformation. Which of course begs the question, where does the transpose come from? Can we do something to a linear transformation to get the matrix A transpose? And in fact, we can do this using dual spaces. And this is really cool, usually something not taught in linear algebra, or sometimes as an optional section. And so now let us define the transpose of a linear transformation. And for this, I'd like to remind you the notion of a dual space. So definition, V star, is just the set of linear transformations from a vector space to the field. And so it's this F that's very important. So press F to say field. In particular, what makes this different from linear transformations is that we're making sure that the output is a number, not just a random vector. All right, how can we use dual spaces to define the transpose? Well, first of all, let T be a linear transformation from V to W. Linear transformation, so you can think of two vector spaces, V and W, and T being the plane between the two, like an airplane. And remember, to calculate A transpose, you would like to flip things. You flip the I and jth entry of A. Similarly, to define T transpose, somehow you're flipping not only the spaces, but also the action. So define now T transpose to go from the shadow space, so the dual space of W, going from W star to V star. So somehow T transpose goes from those weird shadow spaces, it goes from W star to V star. And in particular, let's see what the input and the output is. So the input, it's something in W star. But remember, elements in the dual space, they're linear transformations. So the input is some linear transformation from W to the field. G goes from W to F, and that's the input. And what is the output? So T transpose of G, well, it's an element in V star. So in particular, T transpose of G, this whole thing, is another function. So output, T transpose of G, well, that's in V star. So in particular, T transpose of G, well, it's a linear transformation from V to F. So it's very important. This T transpose takes a function as its input and spits out a function. And now we can finally give you the correct definition. So T transpose, again, goes from W star to V star. And what is T transpose of G? So G is in W star, and it gives you something in V star. In particular, T transpose G, it takes a vector in V as its input. So X is in V. And here's a cool thing. All it does, it flips the two things. Just like the transpose that flips things. So T transpose G of X is G of T of X. And that is now the definition of transpose. And you're like, what the hell? What does it have to do with the nice thing where we flip things in matrices? Okay, but just to give you a picture, so suppose you're fixing a vector. So if in one thing G fixed, so picture. If you fix G, then what does this look like? Well, there are two ways of going from V to F. On the one hand, you can go through W. So x is in V. Then, using t, you can get a vector t of x. And then using g, you can then get a vector g of t of x. On the other hand, t transpose of g is like a direct flight. It takes x and directly gives you g of t of x. And that's t transpose of g of x. So you see, t transpose of g takes a vector g in w star as an input and spits out a vector it takes a linear transformation g as its input and spits out another linear transformation t transpose of g. All right, this is all in good, but as I said, what the hell does that have to do with matrices? Well, now let us show the following. We'll show that if A is the matrix of T, it turns out the matrix of T transpose will be A transpose. And this is really the cool, freaky reason where A transpose comes from. And so here's our theorem. Very well. Let's see if this works. Much better. So here's a theorem. And I know, lots of assumptions. Because we first want to build the matrix of T, and then we want to build the matrix of T transpose. So let T go from two vector spaces, V and W, be a linear transformation. To define the matrix of T, you need an input basis and an output basis. So let beta be V1 up to Vn, be a basis of V, and gamma, which is W1 up to Wf, be a basis of W. Using that, we can define the matrix of T. So let A be the matrix of T, and it goes from beta to gamma. That's on the one hand. That deals with V and W, remember, because T goes from V to W. All right, on the other hand, T transpose goes from W star to V star. In particular, we need bases now for V star and W star. The good thing is, though, it's very easy to construct bases of dual spaces given original bases. That's the whole junk about the dual bases. So now, let beta star, let's say F1 up to Fn, be the dual basis of V. So the point is, beta star, it's a basis of V star. All right. Just to remind you, what is a dual basis? It's just a set of functions or set of linear transformations where Fi is 1 on Vi and 0 everywhere else. So in this case, in this picture, Fi is just like an indicator function almost. It's 1 here and then 0 everywhere else. That's supposed to be 0. So Vj, in other words, Fi equals, so Fi of Vj, if j equals I, so if they coincide, that is 1, else it's 0. All right, and all right, so that is the dual basis of V. I guess, no, dual basis of beta, sorry. So it's a dual basis of beta. And similarly, we can have the dual basis of gamma. So gamma star, which is G1 up to gm be the dual basis of gamma. And the point is, this becomes a basis of W star. And that's good, because now we have gamma star being a basis of W star, beta star being a basis of V star, and the point is, using those two bases, if you calculate now the matrix of T transpose, you will get A transpose. So then, T transpose, going from gamma star to beta star, equals A transpose. And I know, lots to swallow, but all we're saying is, under the most natural of conditions, if T has the matrix A, then T transpose has the matrix A transpose, which gives us, again, a very profound meaning of A transpose. It isn't just a thing where you flip it. It's something very deep that has to do with dual spaces. All right, and you may say, why is that true? Well, let me show it to you, and it's a really nice proof. Not too long, just a couple of indices, that's all. And by the way, in another video, I will show you how to explicitly determine the matrix of T transpose, and hopefully it'll convince you that you indeed get A transpose. So, why? Well, how do you find the matrix of a linear transformation? Well, you just apply your linear transformation to the basis vectors of the inputs, and you write this in terms of the basis vectors of the outputs. So, here the input basis is gamma star. So what you have to do, you have to calculate T transpose at the vectors in gamma star, which is T transpose of G1, up dot dot dot, T transpose of Gj, up to T transpose of Gm, and you express it in terms of the vectors in beta star, which is just F1 up to Fn. So again, the goal is you calculate T transpose of Gj and write this in terms of F1 up to Fn. And I would like to remind you of really cool facts, so that I may have talked about before. It turns out the reason dual bases are so nice is that we have a very nice decomposition. Any vector in V star we can express very easily in terms of that dual basis. So recall, here's a little fact. So if F is in V star, then F can be written very easily in terms of the Fi's. Namely, all you do, you evaluate F at the basis vectors Vi, and you write it as a linear combo of Fi. Why is this important? Remember the definition of T transpose Gj. I love that word because it sounds like juje in Farsi, and that means like chicken breast. Oh, I'm hungry. But anyway, so T transpose of Gj is precisely in V star, which means we can easily decompose it in terms of the Fi's, which remember, that's what we want. So this equals to the sum from I from 1 to n of T transpose of Gj evaluated at Vi times Fi. And as I said in math, you better use your assumptions. So one thing we definitely have to use is the definition of T transpose. And soon we'll use something else as well. And the definition of T transpose means you just flip them. So this is really the sum from 1 to n of Gj of T of whatever that vector is. So T of Vi times Fi. All right, very good. So we already have this. So really, all that's left, if you want, is to calculate this. Because this precisely gives us the, if you want, ijth entry of your matrix. All right, what's the other thing we haven't used yet? Well, we have not used the fact that T has a matrix A. So I like to remind you the matrix of T from beta to gamma, the way you do this, you evaluate T at the basis vectors, and you write this in terms of the output vectors. And this is V1 up to Vm. And this entry, it's precisely AKI. Unfortunately, I have to introduce this notion. So, in particular, T of Vi is now equal to the sum of K from 1 to M, AKI, WK. Again, you better use the matrix A at some point. Otherwise, how can you show this? Okay, and that was part 2. And that's good. So we have TVI, and now we want to evaluate GJ of that. So GJ of TVI, that's GJ of that sum K from 1 to M, AKI, WK. Now, the GJs, they're linear, so we can just pull it inside of the sum. That's the beautiful thing about linearity. It's like this harmony that's going on. So AKI, GJ of WK. And if you want, you can express it as follows. Let's see. I think I can erase this part. If you don't like the sum, let's just decompose it. So that is, if you want, AKA 1I, J of W1 plus A2I, GJ of W2 plus blah 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 plus AJI, GJ of WJ plus dot 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 plus, in this case, AMI, mon ami, and GJ of WM. Why is that important? Because remember, the GJs, they're dual basis vectors. In particular, they're either 0 or 1. And when are they 1? Precisely at the job WJs. So GJ is 1 at WJ and then 0 everywhere else. In particular, let's look at those terms. This becomes 0. This becomes 0. This becomes 1. This becomes 0. And then, after the dust has settled, in the end, the term that we want, GGJ TVI, just becomes AJI. In other words, what do we have? T transpose of GJ is just AJI FI, which looks almost like A transpose. In fact, it's the ijth entry of A transpose. So, just to summarize, what do we get now? I think that's part 3. So T transpose of GJ equals the sum from 1 to n of AJI FI, and that's the ijth entry of A transpose IJ FI. And remember, what does that mean? Precisely the definition of a matrix. You evaluate T transpose at your input vectors, you express it as your output vectors, which tells us that the ijth entry of the matrix of T transpose, I'm almost done, so this like time to me to stop. What this is telling you is in fact the matrix of T transpose from gamma star to beta star, it's precisely A transpose. And this concludes the proof. I know it looks very complicated, but it's really just a matter of using the definition of a matrix. You evaluate T transpose at the input vectors and express it in terms of the output vectors. So here the input vectors are Gj, the output vectors are Fi, and then you get precisely your result. Alright, I hope you liked this transpose extravaganza, and I hope things cleared up for you now. And if you want to see more math, please make sure to subscribe to my channel. Thank you very much.